Okay. Well, hello everyone, and welcome to episode number 11, season 2 of the Biotensegrity Party, which is organized by the Stephen M. Levin Biotensegrity Archive. And today our special guest is Graham Scarr. We're so happy to have you here as a guest, Graham. Graham is also a co-host. So Graham's going to be talking about the value of tensegrity models and other things as well. I'm Chris Morita Clancy from the unceded territories of the Coast Salish Nation, living in Deep Cove outside of Vancouver, BC.
And I'm Susan Lowell de Solorzano from the United States colony of Washington, D.C. And Graham is coming from Nottingham. Graham, just wave hello, and then I'll do the...
that's Nottingham, UK. Sorry, I was distracted.
No, thanks. We're out of order today anyway. Anyway, it's our intention to promote and share the biotensegrity concept with as many people as possible and to include you all in that mission. The Biotensegrity Party is an all-volunteer production of the Stephen M. Levin Biotensegrity Archive, which is a not-for-profit organization whose mission is to educate, raise public awareness, build community in the field of biotensegrity, and to foster and forward discovery, research, and understanding in the areas of science, health, and medicine.
Okay, so let's introduce our team. We wouldn't be doing it. We wouldn't be able to offer you the tea parties without this fabulous team that we have. So Mariana Barreto, coming to us from Mississauga, Ontario. Hi, Mariana.
Hello, everyone.
And we have Patricia Hopper from Seattle, Washington. And Patricia, I don't see you on my screen. I hope you're...
Hi there.
Oh, there you are. Hi, Patricia. Okay, and we have generally Lisa Babiak is also here. She is not well today. So hi, Lisa, if you're watching, we hope you feel better soon. And Gwen Cornish from Creston. Is that right, Gwen?
You bet. Hello.
And we have Neo Judy from Lancaster, Pennsylvania. Neo, hello.
Hey, fellow partiers.
And of course, we have all of you here today. We're so happy to have you here joining us. Thanks for your patience with our technical difficulties. Now, to get us started, I'm going to pass the mic over to Steve. Stephen Levin, the father, the originator of biotensegrity. Welcome, Steve.
Well, thank you so much. I guess I'm going to be doing the toast today, but before I do that, I have a few words I'd like to say about what has been going on there have been a few incidents in the last week and during the episode on common misconceptions that have concerned me, and I think I have to address them. Scholarly debate and hashing out differences of opinion are exactly how science moves along. And it's a bit messy and at times a real mess, but that mess is a necessary mess. However, being messy should not spill over into being boorish. One of the aphorisms I use when I have my signature block is that the purpose of science is not to find the answer, but to sort out the bad answers. And that can only be done by never accepting any answer without challenging it over and over. Unquestioned answers is the obverse of unanswered questions, and it's two sides of the same coin. And so both are subject of scientific inquiry and discussion. And so when you get things like dogmatic statements such as stretching is bad or stretching is good, they must be challenged. It's really what science is all about. And anyone who thinks we have to agree on everything just doesn't understand science. Doubt and distrust of dogma is the beating heart of science. Not only are we allowed to disagree, we must disagree. in order for the science to move forward. But scientific debate should be collegial and scholarly and not a mess. There is no place for personal attacks, ad hominem assaults, words like "you're wrong," implications that other person was ignorant or incompetent or purposely deceptive or some such accusation. Questioning the value of someone's claim is not the same as questioning the value of them as a person. And questioning the value of a given statement is very different than attacking the person who made that statement. So no one should feel comfortable about asking a question, as there are no bad questions. And equally, nobody should feel uncomfortable about challenging any statement, anyone, especially by us so-called experts and authorities. We're all equal here, and each of you bring a level of competence and knowledge that makes you special and unique. Being discourteous to someone asking a question or challenging answers is an intolerable offense in our community. So ad hominem attacks, boorishness, disparaging remarks, intimidation, bullying, or coercion is unacceptable in any form. I've been challenging authority all my life, and I have the scars to prove it. To quote my hero of heroes, Albert Einstein, to punish me for my contempt for authority, fate has made me an authority myself. So to quote another hero of mine, Harry Truman, who was the president when I first entered college, if you can't stand the heat, get out of the kitchen. So you got to doubt authority and ask questions, and that's what we're supposed to do. Now, sometimes you won't get all your questions answered right online. The Biotensegrity archive is designed to answer those questions. And what you have to do is contact us, and we'll put you in touch with somebody who may know something about what you're doing or asking, or if not, they'll help you work it out because they want to work it out too. And with that, I'd like to just give a toast to all of you who have come and give your time and effort to do this and become part of this very scientific community. They're rare. This kind of thing is a rare occurrence where everybody can get together congenially and discuss these things. So, l'chaim, everybody.
L'chaim.
Cheers.
Cheers.
Now get on with the fun.
First, I want to thank you, Steve, and just really to say that my experience of this community has enabled me to ask questions. And this word hierarchy that I first heard from you. This is truly a hierarchical community where we get to learn from each other. And really, this is because of who you are, and it touches me and my heart so deeply. So thank you.
Well, thank you for all coming. You know, I'm an old man now, and my job is to get you people to become the experts, so that I could sit back and enjoy the accolades from other people. So, but without you, you know, I have no legacy. So I really depend on you people to carry on my work.
Thank you.
I start as my work.
Thank you, Steve. So we're going to move on with our sponsors. Susan, today I believe you'll be sharing our sponsors with everyone.
Yeah, and I'll make it quick because just because we've got so much going on today. We do want to thank Handspring Publishing in East Lothian, Scotland, who has been backing us up since the beginning. There's going to be a coupon code in the chat if you're here live with us on Zoom. They've just got a bunch of wonderful books, more coming out all the time. A lot of the authors of Handspring books are here with us every week. That's too many people to probably name, but I can see Eleanor, Graham, Elizabeth, Chris. Steve's got entries in several books. I actually have a book. Anyway, we want to thank Handspring. Embodied Biotensegrity is Chris's wonderfully resourceful organization, educational organization. If you really want to learn about Biotensegrity, check out what her group is doing. It's just, I make it to those events whenever I can. We Flow Therapy with Mariana Barreto. She did an amazing free masterclass recently. Her understanding of how to apply the concept of biotensegrity in therapy is just second to none. It's amazing what's happening with those kids. The International Biotensegrity Congress coming out of Brazil starts today. The wording in the discount code that's going into the chat is that it's 15% off through the 23rd. So maybe it still works today if you haven't signed up. Ana Altsubo is going to keep that stuff up. I think it's starting right about now. And she's going to keep it up for several months. So it's going to be a really good deal. The Fascia Hub, Jan Dwartha's organization, they've got a full day event on the fascial foot coming up on the 8th of May. So take a look at that. Matrix repatterning with George Roth, who was here a couple of weeks ago. Wonderful tea party. If you haven't looked at it, it's on the YouTube channel. Integrated Biotensegrity in Alberta, Canada. And Lisa Babiak, our usual volunteer who's not with us today, does some great courses out of that organization. Pretensed in Holland. Gerald de Jong's really cool models, Tensegrity models. There's also a discount code in the chat for his stuff, as there is for Artifact Pro. And that's Fernando Tejero's models, which include really amazing models, really high quality of like the pelvis and stuff like that. So he's working closely with Dorothea and the Tom Flemons Archive to bring you some of those concepts as well as his own. So check out the chat and you can find the discount codes. Back over to you, Chris.
Thank you, Susan. And so let's get on with our show. First of all, I will introduce you to Graham Scarr, who's a chartered biologist and retired osteopath, a fellow of the Royal Society of Biology and fellow of the Linnean Society. And he has an interest in the mechanics of living structures. Graham has developed new models that progress our understanding of the structure, function, relationship in the human body. He's the author of, I wish I had my book here to hold it up. Do you have it, Graham? He's the author of the Handspring book, Biotensegrity, the Structural Basis of Life, and several scientific papers. And it is my delight to call Graham up to the stage to share his presentation with us today. I've been really looking forward to seeing this, Graham. And before you begin, Graham, I'm going to invite everyone to turn their videos off, and that gives our YouTube audience a much better picture. If you're there on YouTube, please pop your name in the chat. Let us know where you are. Pop your questions there. Neo is going to be bringing them over to the Zoom chat. And if you're here on Zoom, please put your questions in the chat for us. Thank you all. Go ahead, Graham. Sorry for interrupting you there.
That's all right. Thank you very much, Chris. I'll start the sharing straight away. There we go. So welcome to the value of tensegrity models and other things of interest, where we're going to be looking at some simple things and show how they help to elucidate the biotensegrity concept, understand the human body and the whole of biology better. This session is going to be a bit longer than usual, so there'll be a lot of information I'm passing through. Much of it is in my book. There's also quite a bit of new stuff as well, so I hope you find it interesting. Now, as an osteopath, I recognize things in my patients that just didn't make sense. For example, the huge number of changes that follow even the simplest of movements seemed impossible to comprehend. And the way that every part of the body has an influence on every other part was something that I always took for granted. but was never properly explained in the textbooks. So when I read an article in an osteopathic magazine that described a different way of understanding the human body, the thing that really caught my attention was a picture of the, it's not going to change. Why doesn't the slide change? Oh, it worked before in a practice run.
Graham, if you hit, are you hitting your space bar?
No, should I be doing? Doesn't work with the space bar.
I can see your cursor and a little tiny arrow to the right at the bottom.
Can you really?
Yeah, right now, right there. Click there.
Yes.
And let go. There we go.
Right, do I have to use that every time?
Yeah, bring your cursor back down so I can see your cursor, but you cannot, correct?
Okay.
That's
Right.
take it the other way. Go
Oh, now it's working. Now it's working normally. Thanks for that.
Okay, great.
Right. Yeah, so this is a picture that I saw in a magazine. It's a tensegrity structure, Tensegrity Icosahedron, or T icosa. The drawing is actually incorrect. There's some errors in it, but it just enthused me. I wanted to know more about this, so I had to make the thing. And once I'd made the model, then I managed to find information from Steve and contacted him, and then produced other things because find out how does this relate to the human body. So this is one of the first models I made of picture of the upper limb made out of tensegrity, showing the shoulder, the elbow, the wrist, the hand, and the fingers, all made out of tensegrity. Now this is a life-size model. And by holding the hand, it's just like holding the hand of a real person, because the whole thing moves really easily. It's fluid. It's nothing like the skeletons we see in the classroom. And from this, I was completely sold on the idea that tensegrity had some value in understanding the human body. And the next step was to get a plastic model of the upper limb and to go to the textbooks and find out where all the muscles and fascia attachments were. And I'd done all this before when I was a student, but I looked at it in far more detail to make this thing here. It's not a tensegrity, but it got me into looking at more detail. So by looking at the textbooks, reading lots of papers on the subject, scientific papers on the subject, I found there's an enormous amount of information out there that relates and supports biotensegrity, but it's been hidden away for many years. So I wanted to look at the elbow. The elbow is commonly described as a hinge joint and third-class lever, where the bones grind against each other during motion. But this is nonsense. It is also thought that the joint moves through a system of flexor muscles and extensor muscles, but this is also questionable. For example, one of the flexor muscles, brachioradialis, is always active in forced and rapid flexion and extension. Rather bizarrely, it is supplied by the radial nerve, the nerve that innervates triceps and Anconius, its supposed antagonist. And Anconius is also interesting because this little muscle is always active before the much larger triceps, all of which suggests that something else must be going on. Now, when brachioradialis contracts, it exerts a distraction force across the joint surfaces between the ulna and the humerus in the direction of the blue arrow. And this would be contained by triceps, Anconius, and the posterior fascia. This is well established in the textbooks, by the way. So it may be that brachioradialis and Anconius act as part of a rapid response unit that regulates pressure across the joint surfaces, allows them to glide against each other without being compressed, or even maintain a certain amount of separation between the bones. So the biotensegrity concept explains how the bones can float or be suspended within the tension network of muscles, fascia, and other connective tissues, and remain completely stable throughout. There's no bending moments, no shear stresses, no levers. And of course, when I was developing the models to understand this, I produced this one here, which is not anatomically correct, but it shows a principle of the floating bones in a tensegrity elbow. And a few years later, this model was picked up by a PhD student working in NASA called Steve Lessard, who developed this plastic tensegrity model of an elbow and used it in the development of new types of robotic joint for use in the exploration of space. And since then, they've also produced a complete limb made out of tensegrity that also has potential medical uses as prostheses. So this is why I emphasize the value of playing with simple models, because you never know where they're going to lead to. So let's get back to some basics. The picture in the model shows a triangle. What it's showing is 3 ball bearings held together by these magnetic sticks. And the magnets are pulling the balls together, but also their physical structure holds the ball bearings apart. And triangulated structures are really stable, the most stable structure there is. And putting lots of them together produces this hexagonal arrangement, triangulated hexagons, a very efficient close packing arrangement. So we'll look at these picture on the left, which is a collection of ball bearings sitting in the bottom of a dish with a curved surface. Now, all these ball bearings are influenced by gravity. Gravity is pulling them downwards, but they can't all come downwards. They have to head towards the center, but they can't all be at the center at the same time, which means the outer ball bearings are pushing on the inside ones, and the inside ones are pushing on the outside ones to keep them there. The whole arrangement automatically balances into this triangulated hexagonal pattern. It's about geodesic geometry, which is forces of attraction and repulsion, tension and compression, pull and push, always act in straight lines, geodesic geometry. They form a close packing arrangement. It's the closest they can reasonably get to each other and exist in a state of minimal energy. If you fall asleep, forget everything I've said. Remember this picture. The hexagon appears throughout biology in bubbles, always joined together to form hexagons, where the angle between them is 120 degrees when looking from the top. Within the eye of the beetle, we see hexagons. Within muscles, the molecules of actin and myosin form this regular hexagonal pattern within myofibrils. At the most basic level, atoms interact with each other through the forces of attraction and repulsion, but we label them as van der Waals forces, hydrogen bonding, covalency, steric repulsion, but they're all actually attraction and repulsion. And they spontaneously organize themselves, self-organize themselves to form crystals and flexible molecules. And the same principles apply at every size scale. That is what tensegrity is based on. The balance of compression struts floating within a tension network of cables under tension. Tension and compression. And the same principles apply throughout. So now we're getting into 3 dimensions, and we'll look at the Platonic solids. Widely recognized by the ancient Greeks as an explanation for everything in the universe. And the Platonic solids are interesting. There's only 5 of them. And of course, they don't have to be solids. It's the outline we're looking at here. But each one, the faces of each one are all the same. And the faces all have 3, 4, or 5 sides. And we'll see that the tetrahedron, the octahedron, and the icosahedron are all constructed from triangles. And once again, triangles are really important because of their regular shapes of stability. Excuse me. And by dividing each of the faces into smaller triangles, eventually they get closer to the appearance of a sphere. And a sphere is important because it occupies the maximum volume within the minimum surface area. It's a very energy efficient shape. And the interesting thing about some of the Platonic solids is that each one can be packed inside the other. They close pack. So the tetrahedron consists of 4 balls close packed together. This is a higher level tetrahedron, the blue one, showing the yellow octahedron within it. Particular type of cube, but they all have this same packing arrangement. And I mention this because this is what biology is all about. Biology is about shapes inside shapes inside shapes. And you won't see any of these shapes in the body. It's a principle I want you to get hold of. The icosahedron and dodecahedron pack in a different way, and we'll come to look at those later. So all these shapes naturally occur in nature as crystals. These are octahedra, cubes, and dodecahedra. Now, a really interesting thing about the tetrahedron, this one here, with its 4 sides and 6 edges, is that by adding more tetrahedra next to it, we produce a tetrahelix. This is a left-handed tetrahelix and a right-handed tetrahelix. In other words, chirality, left and right-handedness, emerges out of the tetrahedron. And the tetrahelix is the simplest geometric helix there is. But that also presents a paradox, because A, B, and C show tetrahelix with more complex helixes inside them. It's one of those strange things that happens in geometry, the simplest containing the more complex inside it. We'll look a lot more with the tetrahelix. And chirality is also a feature of tensegrity. Here we see a right-handed twist. In the T icosa here, the yellow struts form a right-handed twist and the green struts form a left-handed twist. So chirality is balanced, left and right-handedness, in the Tensegrity icosahedron. And tensegrity is an example of geodesic geometry, where the tension and compression, which we can't see because they're physical representations of the struts shown by the struts and cables. It's also close packed because they get as close as they can to each other and exist in a state of minimal energy. So where does this occur in the body? Well, the helix is a very common biological motif at every size scale. This is a structure of collagen type 1. And collagen is the most widespread structural protein in the body. And in the most basic level, amino acids join together to form a chain, a procollagen, and they have a left-handed twist about them. And 3 procollagens twist together to form a right-handed twist of tropocollagen. And the tropocollagens close packed together to form a staggered microfibril, which altogether comes closely to matching relates to the Fibonacci sequence and golden mean, which we'll talk about later. And they close pack within a collagen fibril, a fascicle, and in this case, a tendon fiber. So collagen, with all this helical hierarchy going on, is a very common, most widespread protein in the fascial tissues, all the connective tissues. And another little interesting thing, which I'm going to show you, is that inside the tetrahelix, one of those more complex yellow helix here, the left-handed helix, and closely matches the chain of amino acids in the procollagen. And the 3 chains of procollagen that form a tropocollagen, the space in between actually forms a perfect tetrahelix. So simple geometry appears in complex biology. We don't see it on it every day. We can't even see it on a dissection, but this is what happens. This is why learning about simple geometry is important for understanding the more complex aspects of biotensegrity. And the value of helical tubes at a higher scale is that they don't buckle. So this plastic tube here will buckle, which means that fluids can't pass through it. But helical springs, tensegrities, maintain the spacing between. This is a Tensegrity helix. This one here, this model here, consists of 6 T icosas all joined together. And what emerges out of it is that if we paint certain struts, the left ones form a left-handed, the white ones form a left-handed helix, and the red ones form a right-handed helix. The helix is everywhere. And moving up a scale, we get to crossed helical tubes within tubes. Now this is a nice picture here showing the close packing of things in the thigh. It's a dissection very much cleaned up. You wouldn't see this if you were to do a real dissection, but it nicely shows this thing about tubes inside tubes inside tubes. It just so happens that tubes are everywhere. The esophagus, the intestinal tract, the urinary tract, the walls of arteries, muscles, muscle fibers form tubes surrounded by endomysium, and groups of endomysial tissue coupled together to form perimysial fascicles. And the perimysial fascicles are enclosed together within the whole muscle, within the endomysium, with the, beg your pardon, the epimysium. And the collagen fibers within all those tubes form crossed helical arrangements, where the left-handed helixes form an angle of 55 degrees, and the right-handed helixes form an angle of 55 degrees, or thereabouts, approximately. And they're not forming layers, they're forming laminae. Each one, so the left-handed helix is in one lamina, the right-handed helix is in another lamina. And the interesting thing about 55 degrees is it balances the tendency of the tube to lengthen or to increase in width. Very important if you want to increase the volume. And this angle of 55 degrees also appears in the helix of the heart. The heart muscle is a helix, and the collagen fibers are aligned in the same arrangement. Now you may have noticed that most of the pictures have little captions at the bottom. Most of the pictures here are my own, or they're taken from other people like Rory James or Wikipedia. Many of them are copyright to Elsevier or Handspring Publishing, except for this dissection model here. Now this picture appears in several places on the internet, but no one seems to know where it comes from. It looks like a Frank Netter picture, but I don't think it is. So if anyone knows where this picture comes from, please let me know and I'll be happy to give it good credit, because I think it's just a brilliant picture to emphasize so many things. So back to real life. Now, as a cranial osteopath or craniosacral therapist, one of the things we recognize is palpatory phenomena in the limbs, where the limbs appear to expand and contract, to increase in volume and then decrease, and also have a twist about them. It is very slight, very low amplitude, occurs between, say, 4 and 8 times a minute. And there's a good reason to this, which we'll come to in a moment. Now I thought, well, if the alignment of collagen fibers is both 55 degrees, that would explain how it could expand and contract, but wouldn't explain the rotational component. And I puzzled about this. Well, I had to perform an experiment. So I produced this apparatus here, which is essentially nylon strings connected to a plate at the top and a plate at the bottom. And the strings are related into a left and right hand helix. In this case, they had 10 degrees and 22 degrees. And the lower plate is connected to a spring with a protractor around it. So what I did was put a balloon inside the helix and then blow it up, put air into it. And lo and behold, the helix expanded in width and the lower plate twisted. I think it was about 15 degrees, but it demonstrated proof of principle. And from then I had to think, well, what's going on here? Why would this happen? Because there are very few studies on the angles of collagen within the human limbs, have sorts of different angles, they don't agree. But if 55 degrees angles occurs in the tentacles of the octopus, the body walls of fish, dolphins, whales. Just this morning, I got a message from Doug Johnson to tell me about the bones of pterosaurs. These are flying dinosaurs from 65 to 120 million years ago. Inside the bones, they found that the trabeculae are aligned in helical arrangements, just confirming that helix is everywhere. So all this stuff is up to date as best we can do it. Now, arteries expand and contract in an oscillating manner because blood pressure, and they help to increase. No, let's start it again. Now, blood pressure changes all the time. It's not constant. It goes up and down all the time. It's related to the Traube-Herring-Meyer waves. These oscillations, which are controlled by the sympathetic nervous system, enable the arteries to expand and contract in a rhythmical way. This is happening all the time. It's related to breathing, the Traube-Herring waves, and the Meyer waves on the much slower 4 to 8 frequency, comparable with what we feel in the limbs. Now, of course, I wanted to try this out for myself, so I produced this construction here, which is a, oops, I knew that would happen. Here we go. It's called a Platysma Graph. And what we do is put the forearm into this machine, and inside is a elastic bag full of water at the body temperature. And as the limb expands and contracts, which it does, so the change in volume can be measured in this scale here, which in this scale is down to 10 microliters. That's 0.01 of a milliliter. But it is sensitive down to 2 microliters as well. And what I found as I was breathing, breathing in, the volume increased, breathing out, it decreased. And the blood pulse itself, just at the bottom level, 2 microliters, could see how the volume expanded and contracted. So, but the Meyer waves, which are much slower, couldn't be measured because it needs some fancy bit of kit, which I didn't have. But all these oscillations are going along at different frequencies all the time. Why would, this is well recognized in intensive care units in hospitals, but they don't consider it much of importance. But why would this occur? Why would that rotational component? Well, it turns out the pangolin might provide an answer. The pangolin is the only mammal that has these scales on its outer surface. And again, it has left and right-handed helixes in the body wall, which are the same. But in the limbs, the left and right-handed helixes are different. Now, just supposing, and this is pure conjecture, supposing the alignment of collagen fibers within the human limb is similar, because geometric patterns and shapes don't just appear out of nowhere, but out of some basic principles of self-organization. So as I say, this is a pure conjecture. It now waits for someone to find out, because nobody knows, because nobody's looked. So there's something for the future. So let's go back to the tetrahedron. See what other revelations it's got for us. This is a wire model of a tetrahedron dunked in soapy solution. And when they pulled the model out, so it formed a soapy film projecting inwards from each of the edges. And they all meet together to a central angle called the tetrahedral angle, which is 109.47 degrees. Now, if you connect 3 or more bubbles together, edges always meet at these tetrahedral angle. You see the tetrahedral angle here. I hope you can see it. Another one here. All bubbles, 3 and above, meet at this tetrahedral angle. Of course, from the outside, from looking above, they still form the hexagonal angle, 120 degrees. But looked at from the side view, you can see it nicely here. What does that mean? Well, this picture here shows a trabecula of the neck of the femur in human bone, showing all these little spicules, which do have different angles, but collectively average the tetrahedral angle, about 109 degrees. honeycomb of the bee. This is a cross section, greatly magnified. The cells on either side joined together through the tetrahedral angle. Simple geometry in complex biology. And Natalie Resnikoff, who did this research on the bone, she will be joining the Biotensegrity party towards the end of May. So she'll be able to tell us even more about this. And doodling with tetrahedra, all it consists of is 6 edges, 4 sides. But as we saw before, when we join tetrahedra together, they form a helix with chirality. And just playing with tensegrity models and icosahedra produce these two comparable structures, which also have chirality. I had no idea exactly what the significance of these is, but just by playing with these things can take us into all sorts of unknown places. The icosahedron naturally occurs in the outer capsules of viruses. All viruses can be divided into spherical viruses, which are icosahedra, or rod-shaped viruses, or essentially helixes. So these viruses here, which I think may be polio, this one here shows the arrangement of proteins which have a Penrose tiling pattern based around the icosahedral template. The icosahedron also appears in radiolaria in the sea and pollen grains of morning glory. And this model here, the icosahedron relates intimately with the golden ratio, or golden mean, 1.618, which I had to demonstrate with this picture here, this model here, which actually copied off Susan Lowell. Forgive me for not giving you credit. Shows the yellow strings marking the outline, the edges of the icosahedron, and by joining up some of the vertices, they form these interlocking plates where the width of each one and the length of each one relate to the golden ratio, 1.618. And similarly, the blue octahedron on the right, enclosed within the yellow octahedron, is relationship 1.618. The golden ratio is an irrational number, and irrational numbers are key to understanding many aspects of the geometry and mathematics of biology. And the Fibonacci sequence, which derives from the golden ratio, naturally appears in the close packing arrangement on flower heads. It's a very efficient packing arrangement during growth. And they don't just form by one packing next to the next one to the next one. It's a very complicated arrangement, produces this nice thing. And the same with the spiral, equiangular spiral of the Nautilus. And of course, each Nautilus won't be an exact replica of that spiral. You're collecting different Nautiluses, nautili together. The average between them matches the golden ratio. And we've also already seen the limbs of the pangolin. So, little refreshment. Moving on to Tensegrity model. The first recorded note of a Tensegrity model is this picture on the top left, which is made by the artist Carlis Johanssons, a Latvian who changed his name to Carl Iogensen. And he made these several Tensegrity models, and a great artist as well, great painter, and he exhibited them in an exhibition in Moscow in 1921. But he was a keen supporter of the Russian Revolution, and because Tensegrity didn't seem to have any functional value, he left them behind, and they generally got forgotten about until the 1990s. But in the meantime, the young artist Kenneth Nelson, who was a student of Buckminster Fuller, he produced this Tensegrity model here called the X-piece, where the wooden crosses are suspended within the tension network of cables. And this was the start of what we now know as Tensegrity. He went on to a great career producing fantastic Tensegrity models, including this one here, which is a picture of the Needle Tower, which is 60 foot tall, stands outside, or used to stand outside, the Hirshhorn Museum of Fine Art in Washington. Unfortunately, it's now packed away in boxes, and who knows when it'll see the light of day again, but I hope so too. Now, Stephen Levin, that's the chap on the top right. You can always tell Stephen by his hat, which is different every day. Well, he, as an orthopedic surgeon, he recognized things at the operating table that couldn't be explained by conventional mechanical theory. And so he set about looking for alternatives by examining the skeletons of dinosaurs and other animals in the Smithsonian Museum of Natural History in Washington, DC. And because the Smithsonian Museum is very close to the Hirshhorn Museum, it's right across the mall, and Stephen Levin was a keen art lover, he got interested in both the dinosaur bones and also Snelson's Tensegrity Tower, Needle Tower, and realized that Tensegrity explained not only how the huge weight of dinosaur heads could be suspended so far from their body, but also applied to the whole of biology. And he's been writing and talking about it ever since, as we heard at the beginning of the program. So the Tensegrity Icosahedron, or T. icosa, offers multiple possibilities for playing with models. And these are some of them that I played with. I can't tell you what the significance of them all is. It's still work in progress. The model on the top right was probably the most complicated, difficult model I've ever made. It took me weeks to figure out how to make it, and then weeks to actually make it. Anyway, let's move on. Now, when we see Tensegrity models, they look quite static. You know, they just sit on the shelf and don't appear very much. How can this be a model for the human body? Well, this is where we start, because one of the characteristics of Tensegrity is that it displays auxetic behavior. So by compressing, holding the ends of 3 of the struts, then pushing them towards the opposite sides, get a slight contraction. The whole structure contracts around a central point and expands again. Not very much, but it's significant. This auxetic behavior was considered impossible 30 years ago because it demonstrates what is called a negative Poisson ratio. But lots of structures now, lots of materials have been made to perform auxetically. And auxetic behavior has been found in bone, tendons, skin, the viscera, and there's so many examples. Because if the body operates as a tensegrity, follows the principles of biotensegrity, it makes complete sense. And this is just more supporting evidence from the world of geometry. Now, the Tensegrity Icosahedron, or T. icosa, is called as such because each of the ends of the struts very closely matches that of an icosahedron. Not exactly, but close. And in the 1960s, a structure called Jessen's icosahedron, discovered by Borger Jessen, who produced a shape that exactly matches the outline of the Tensegrity icosahedron and also demonstrates a slight contraction and expansion. A few weeks ago, we had on the BiotensegriTea parties Lefteri Pavlidis, who produced the Pavlidis Elastigrity, where the entire structure contracts around a central point and expands again. It's not a tensegrity, but it demonstrates the auxetic principle. And the Hoberman sphere starts off here, expands and contracts. And once again, it's not a tensegrity, but expands and contracts auxetically. And I'll show you an example in a moment. I throw this in, I'm not going to go into detail to it. You may have heard of something called the Jitterbug, which was something emphasized by Buckminster Fuller. What it is, representation of the transformation of energy from one state to another. So just like we recognize tensegrity structures are not modeling the anatomy, they're not modeling bones and muscles and fascia. They are describing the principle of invisible forces of tension and compression and how they interact. They're very simple, but they help us to explain the more complex. Now, Jitterbug is one of those simple models. So if we look at the top left here, which is a cube octahedron, it has six triangles and 8 squares, I think, or the other way around. No, 6 squares and 8 triangles. And it's a balance of the internal nucleus in the center balanced by the outer ones here. And if we make a structure like this, which just consists of the shapes, the triangles and the squares, that matches the shape of the cube octahedron, it's actually called a vector equilibrium, and push the top and bottom together slightly, they go from the cube octahedral stage through the icosahedral stage down to the octahedron and eventually to the tetrahedron. I don't show that. And then they expand back through the icosahedron and back to the vector equilibrium, cube octahedral stage. It's a representation, the transformation of forces. So now there's the alert. I'll just stop the sharing a moment, except there's nothing to say. Oh yes. And I'll show you some things about real models. This is a Tensegrity model. It's a chain of the icosahedra joined together. If I press down from the top, you can see the whole thing expands and contracts. Not a great deal, but when we join lots of tensegrities together, we produce this auxetic behavior. Similarly with this model here, it's not a tensegrity, but it shows a principle expansion and contraction from the largest state to the simplest state, all around a central point. And then, better still, the jitterbug. We show the jitterbug. Showing this model here, how it contracts from the cube octahedral stage to the icosahedron to the octahedron and back again. It forms a twist, which then goes the opposite way and back again. So these simple models help to get an idea, a feeling for it. They're not exact representations. It's that impression, this generating ideas, that's so important. So back to screen sharing again, and yes, here we are. No, it's going to misbehave. Right. So joining lots of tensegrities together, we form chains, towers, and modules. That's very important because the human body is made lots of bits, all joined together at different size scales. It's a collection of modules, if you like, just like tensegrities. And this model here shows the hierarchical nature, where each part is made from smaller parts, and represented with the 6 red struts, which are made from a chain of smaller tensegrities, and the strings themselves are also made from a chain of tensegrities. Now, this particular model has 120 modules in it. Each one took 5 minutes to make. You can work out for yourself how long that took. But modularity is really important, because it means we can make models of the spine. The spine isn't a compressed column at all. Because it operates the same in both upright, as in humans, but also horizontally, as in most animals. And because most vertebrates have got pretty much the same things in common, why would an animal with a horizontal spine need a compressed column? It doesn't make sense. Anyway, this model here is a Tensegrity Tower made from a module of 12 different 6-strut tensegrities, or should have, the top one's missing, I think. The interesting thing about this model is by pushing it down slightly, the whole thing expands and contracts in an oscillating way. This goes on for about a minute. I have seen them go on for about 5 minutes. And this model here, which is 2 thoracic vertebrae held apart solely by the single ring of tension. Now, all these tensegrity models, all these models are not exact replications of the anatomy. We're not modeling the anatomy here. what they do is stimulate ideas. They make us think about things. So once I'd made this model, I wanted to find out a bit more. So this one here is one next to it is a human spine with the spinous processes and the transverse process connected together to match what's happened in the multifidus muscles. It's not a tensegrity, just wanted to help me get a better understanding of what's going on here, because textbooks are okay, but playing with real models gets a much better idea. Now, the general view of biomechanics is that the body operates like a system of levers, because that's the idea promoted in the 17th century, and it hasn't really changed much since. But the problem with levers is that they generate bending moments and shear stresses and stress concentrations. And it is most likely that developing tissue would not be able to withstand disastrous consequences of these. Levers rotate around fixed fulcrums, yet bones follow complex helical pathways during motion. In addition, the nervous system is incapable of controlling the huge complexity of joint movements on its own, which suggests that something else must be going on. I'm going to take a slight little deviation to look at closed kinematic chains, or closed chain kinematics, which has got nothing to do with the system of exercises which have a similar sounding name. This is something completely different. Closed kinematic chains are used widespread in engineering since the Industrial Revolution. What they do is consist of multiple bars connected together into continuous mechanical loops. So on the left here, we have a 3-bar arrangement, the triangle, which is really stable, rigid. And here we have a 4-bar arrangement. And the 4-bar is the simplest closed kinematic chain, or CKC, to enable motion to occur in a controlled way. And I'll show you a model in a moment. And we can see the 4-bar in action in the pantograph mechanism. It allows amplification of forces, power, shape, energy, or alternatively, the attenuation of all those things. It's a very useful shape and structure. The artist Theo Jansen in the Netherlands produces these wonderful strand-beast creatures made from multiple couplings of 3- and 4-bar shapes all joined together. This is just a small model. And they walk along the beach that are powered entirely by the wind. They're about 12 foot high. And he's got these things walking around on their own, just as though they were alive, but of course they're not. And this, the bottom here, shows this arrangement of 3- and 4-bar shapes. And one more time, model alert. So let's have a look at these closed kinematic chains. Good spotlight, thank you, thank you. So here's a 4-bar arrangement with joints on them. Push one against the other, the whole system regulates position and motion of all the others in the system. I move it around and get a different pattern of motion. And if we join lots of closed kinematic chains together, we produce something like this, which is actually based on a Penrose tiling pattern. I'm just pushing two structures together, but that force and power has been transferred to cause changes throughout the system. Imagine what if this was going on inside the human body. And lastly, a Jansen mechanism. Come on, behave. Shows how the 3-bar shapes provide a stability that allows the 4-bar shapes to change shape and create movement. And Theo Jansen's models have about 20 or 30 of these all linked up together. Now, at first sight, you might think, well, these are just complex lever systems, aren't they? But no, because in a biotensegrity complex, where every part is made from smaller parts, we have a better explanation for it. Closed kinematic chains are at the heart of tensegrity, where we have the white strings, the white parts causing the stable triangles and the blue dotted 4 bars that enable the motion demonstrated with the auxetic behavior. Where does this occur in the body? Come on, behave. Well, first, before we get to that, there's another model, closed kinematic chains. And here's a jig as I used to make that model for the modeling aficionados, which I hope you're all going to become very soon after this presentation. The cruciate ligaments within the knee form this conversely crossed 4 bar that guides the motion of the femur and tibia in relation to each other. And yes, I know, the reality is far more complex than this. What we're using is a simple model to get an idea to stimulate the little grey cells to think in a different way of what biotensegrity is. Closed kinematic chains have been described in the limbs of horses and humans, where multi-articular muscles, that's muscles that cross more than one joint, they couple the hip and knee joint and the knee and ankle together. They provide a stability that allows the animal to walk and remain completely stable throughout. It guides the motion. One of the characteristics of this closed kinematic chains within the body is that they enable forces and power to be transferred from one part of the system to another in a controlled way. So for example, if we jump from a standing position, we can't go very high. But if we crouch down and then jump upwards, we can go much higher because we're using the muscles that cross the hip joint and the knee joint at the same time to transfer their power down through the knee, down through the ankle to the foot and enable a much greater range of motion. And imagine the same principle is occurring throughout the body, where forces and power be transferred easily through the structures and enable all sorts of things to go on. It's even explained how rock climbers can be suspended from the rock just from their fingertips and move about. Well, the muscles that control the fingers are simply not strong enough to do that. But by transferring their power and invoking the whole system to operate together, we can explain all sorts of things that otherwise are unexplainable. Within the fingers, the closed kinematic chains, the 4 bar, was described by Winslow in the 18th century, the anatomist Winslow. Now, there are not enough muscles to control all different finger positions on their own, and certainly no extensor muscles in the fingers because they are contained within the forearm and hand. So rather than the muscles moving the bones, the standard way of looking at things, what actually happens, the muscles generate the power, which then goes through the tendons to the fascial network in the fingers. And it causes the fascial network to perform its own logic computations that then switch the system between different functional states. The fascia, the connective tissues, perform their own dynamic information processing network, which enables the instructions from the muscle to be transferred towards the bones and change the bones to the position in relation to each other. It's not muscles pushing bones. It's a structure itself that's guiding motion and operating in synergy with the nervous system. And the model on the left is just my attempt to show this, partly successful. So we have to look at all these simple models as a way into understanding the human body and biotensegrity. And I want to look at the temporomandibular joint. This is the first of 2 examples I want to show you. The temporomandibular joint is widely recognized as, well, it's the heart of eating and talking. And traditionally, biomechanics think that the bones themselves, the condyle of the mandible, compresses a disc during mouth opening. And then it compresses a disc and pushes it back during mouth closing. If you look at any book, any article on the TMJ, the first thing they always say is the jaw joint causes more problems than any other joint in the body, but is the least understood. Then away they go with the joint, with the lever model as an explanation for joint motion, knowing full well that a compressed disc will lead to degeneration and pathology. But until recently, they didn't really have an alternative. So let's turn to tensegrity, of which the bicycle wheel is an example. Now, Buckminster Fuller recognized the bicycle wheel. He didn't call it a tensegrity then, but that's what it is. It shows a central hub under compression. Let's see if I can show that. Central hub suspended from the tension spokes from the outer compression rim. And you can see the 4-bar mechanisms within it. And the bicycle wheel is a rigid structure. We want it to stay rigid. But the same principle applies to tensegrity in the wider biotensegrity concept. So I was contacted by a dentist in Cambridge, UK, Helen Harrison, and we discussed about the feasibility of making a model of the TMJ that she could use to demonstrate for her courses and classes. So we obtained a plastic model of the skull and cervical spine and put it together with coloured plastic strings to represent key important muscles and ligaments and fascia that we thought were important to understanding the jaw from a biotensegrity perspective. Now, it is well recognized that the hyoid bone is suspended from the tensioned muscles, fascia, and other connective tissues. And it acts as a stabilizer to allow the front of the jaw to be pulled downwards and backwards. Conversely, the mandible acts as a stabilizer to allow the hyoid bone to be pulled upwards and forwards through the same muscles and influence the pharyngeal tissues during swallowing. And a few years ago, it was recognized a particular thickening of the cervical fascia, now called the mandibular Styloph hyoid ligament, that connects the angle of the jaw to the hyoid bone. And although most ligaments in the jaw joint mechanism receive little functional credit in the textbooks, this particular ligament, mandibular stylohyoid ligament, is considered very important to what we've making our model. So what may be happening is, as the hyoid bone is pulled downwards through the sternohyoid, omohyoid muscles and stabilized, it allows the front of the mandible to be pulled down and backwards during mouth opening. But at the same time, it tensions this ligament, which pulls the angle of the jaw downwards, which lowers the condyle, which takes the pressure off the disc. I'll just say it again, repeat it. As the hyoid bone is pulled downwards, it enables the front of the jaw to open the mouth, to pull the angle of the jaw downwards, to lower the condyle and decompress the disc. The biotensegrity concept then shows how the mandible acts like a sesamoid bone, as do all bones in the body, where it is suspended within the tension network of muscles, fascia, and other connective tissues, where the structure itself guides the system through the closed kinematic chain mechanism, if you like, allows the mouth to assume any position and respond instantly to any perturbations within the system, which occur frequently, normally during eating. It shows how the structure itself is controlling motion and acting in synergy with the nervous system. It greatly simplifies the control process because it evolved right from the embryology stage upwards as a complete system. Just have a little refreshment here. And the final model I want to show you involves curved struts. Now, as we mentioned before about geodesic geometry, about straight lines, connection between 2 points over straight lines, which is what the standard tensegrity models do, connect the ends of the struts and the cables through straight lines. As a cranial osteopath, I carried out a lot of work on the skull, the cranium. It was my interest. And of course, the bones surrounding the brain, the vault, are all curved. And I wanted to know, could tensegrity say something useful about how the bones of the skull function, what they do. So it was about 3 o'clock in the morning, and I was thinking about these things, as you do, and I jumped out of bed and rushed to the other room to get my models to see if I could make a model with curved struts, which seemed a bit of a tall order, but yes, possibly it could be done. So I went back to bed and then spent the next 2 days trying to figure out how to do it, which was much more complicated than I thought. Because as soon as I made the model with curved struts, the whole thing collapsed. It just didn't hold up. It took me a while to configure how to make it with this model here, where the end of the struts allows the strings to be connected on either side, which then allows them to stay upright and maintain the whole stability of the thing. And of course, from tensegrity, from a biological perspective, curved struts would lead to shear stresses inside, cause buckling, and it would collapse. But the body doesn't allow that to happen because each part is made from smaller parts. So I made this tensegrity model here, which has got 2 curved struts, which would buckle if the tension increased. By making each of the curved struts as a chain of tensegrity, a modular chain, the whole thing can distort, change shape, and remain completely stable out as it returns back to its normal point of equilibrium. So from then, it's just a simple matter of getting a plastic skull, cutting the bones of the cranial vault out. The cranial vault is the bones surround the brain. Then constructing a tensegrity structure using nylon string to represent the dural membrane that covers the outer part of the brain and is actually connected to the margins of the bones in babies and children. And because you can't see much going on here, I made this model here made of aluminium and nylon strings where all the bones are suspended. They don't touch each other at any point, represent a tensegrity. So what does this mean? Well, in babies, young children, the bones are separated by quite a space because they're still growing. And it's only until about 7 years of age, they come close to each other and form these sutures, which have interesting curves about them. Got the larger curves here and smaller serrated interdigitations. And I found that these curves are crucially important to making the tensegrity model work. So in babies and young children, the dural membrane is firmly attached around the margins of the bones. This is an inner view of 3 of the bones, and the alignment of collagen within the dural membrane is such the interaction between the collagen fibers and the curvature of the bones causes the bones to be pushed apart by about 100 microns. That's 0.1 of a millimeter. And this remains the case throughout life. So although the skull is thought of being a solid box, most bones remain a certain amount of flexibility between them throughout life. It's only through trauma or pathology when they fuse together. I would suggest this is an abnormal case. And it also turns out that the alignment of collagen within the serrated sutures also is arranged such that the bones will be separated apart. So what does this mean? Well, newborn babies can suffer from something called plagiocephaly, which is a distortion of the bones, probably due to some trauma at birth or maybe after birth. And plagiocephaly often shows an asymmetry of the head, the cranial vault bones. Plagiocephaly often normally resolves itself, but in many cases it doesn't and needs a little help from people trained in the process. And I must emphasize this is not about pushing bones around. Don't go trying this on your next door neighbor's children. Get properly trained before you do this. But anyway, more importantly is craniosynostosis, which means some of the sutures fuse prematurely and allow other bones to grow and lead to a very distorted head shape, which requires some pretty drastic surgery. Now, the causes of craniosynostosis are very poorly understood, generally. Some of them have a genetic link, but that doesn't really tell us very much. The actual physical cause of it is just who knows what. But from a biotensegrity perspective, we can get a better understanding. Now, this dural membrane that lines the inside of the bones also projects down through the center in the middle to form this sheet here, which comes right down the middle, separates the two hemispheres of the brain. And it's continuous with the base of the skull, the dural membrane going down the spine, but also as a lateral projection to the temporal bones. So it connects the bones at the front, the top, the back, the sides, and goes down to the rest of the body. So it may be, before we get to that, tension in the dural membrane is very important to controlling the growth of the bones, because it influences the cytoskeletons of the cells in the dural mater and within the sutures, which themselves have a tensegrity cytoskeleton. And it causes the bones to transform themselves from epithelial cells to mesenchymal cells to osteoblasts that then cause and regulate the growth of the bone. So it may be that some aberrant stresses in the base of the skull or from lower down up through the spine transfer themselves through this dural membrane, the falx, tentorium, to the sutures in the skull and causes abnormal things going on. There's been very little interest in this. The paper was published 12 years ago, lots of citations, but it's mostly written as a tensegrity as a novelty. Hopefully somebody will pick it up and make it useful so that the suffering caused to these children will be alleviated. We'll have to see. Oh, this is a model. This is the picture I meant to show previously. It shows how everything's interconnected from the entire skull, the sutures, interaction with the wavy curvatures, the smaller sutures here, the dural membrane underneath the sutures and the bones, and how the cells within it, which contain helical molecules, of course, all act together as one big unit to explain just what's going on in the skull. So that's a brief run through. It's gone a long time, but it's what I'm doing here is showing you is a personal view of my own models, geometric models, my tensegrity models, and a few others to show how they provide useful ideas. They're not models of anatomy. They're models to stimulate ideas, to get thoughts, to make us look further, think differently. So you won't see tensegrity models in the body. You might see helixes because we saw them in the fascia. So if you do a dissection, you can see these helical collagen alignments. You won't see ball bearings. You probably won't see hexagons, although cells often pack in what look very similar, very close to hexagonal patterns. This is the basis for understanding biotensegrity. There's lots more I could have gone into, but there's not time. Tensegrity, biotensegrity, is not about anatomy, about structure. It's about architecture and how the balance of these forces, attraction and repulsion, tension and compression, pull and push, interact with each other at multiple size scales, using simple models to understand that complexity, which is a vast leap forwards to the standard biomechanical model with its levers and the general things that are put out there for understand. It takes us into the realms of the almost esoteric to the abstract ideas, to things like superstability, which we've been talking about on and off over the last year. I'm not going to go into details of superstability, except I'm going to say that superstability is not the same as pre-stress stability, has been asserted recently. Pre-stress stability is what all tensegrities are, because if we have a collection of cables and struts on the table, they can't do anything. But put them together in a tensegrity configuration, lo and behold, they become self-stressed, pre-stressed, pre-tensioned. They become, if you like, energy modules. just by putting them together in that particular way. And all tensegrity structures are pre-stressed. Superstability is something different. I'm just going to run to a brief little thing. One of the properties of superstability that allows a structure to remain completely stable throughout motion. Now, a lot of these models here can do that as well, but think of it as a biotensegrity context. Think of the jitterbug. Think of the way the 6-strut tensegrity contracted and expanded again auxetically, all the time remaining completely stable. One of the things about superstability is that when we're thinking this abstract way, okay, we're not thinking about real structures here, thinking of an abstract way, is that the cables and the struts can transform themselves from one to the other. So cables can become struts, struts can become cables. And I'm going to stop my sharing here because I want to show you a model or two. Put it on speaker view, Chris, if we could. Right.
You're good now.
Okay. It didn't know my case, but let's take it is.
Okay, let's get somebody else. Maybe Mariana, is this a good picture?
I see you full screen, Graham, right now.
Okay, I can't, but I'll take your word for it.
Graham, change your view. Change your view at the top corner.
All right. Oh, this is all complicated.
You don't have to, Graham, but if you can, if you want.
No, I'm already on speaker view, but I still can't see it. Never mind. Where were we? So, cables and struts in this simple model. Okay, they can't change shape. I wondered what would happen. This is pure experiment. This is pure theory. What would happen if I change all the cables into struts and all the struts into cables? I produce this model here. If you can see the red strings, these used to be the struts. And the 24 cables are now the white strings. But the structure wasn't a tensegrity, so I had to add some more strings to make it into tensegrity, which then made the whole thing much more complicated. Now let's move from that into complexity. This model became inherently more complex. And it is inherent capability of self-replicating systems that catalyze their own reactions to become more complex. They automatically do it. And the body is a self-replicating system, a huge complex network of molecules that are interacting with each other, producing themselves and producing this autocatalytic population. I'm sorry about the big words, where growth occurs continuously and is measured by the amount of nutrients going through the system. So we start with a zygote and then move up through embryology, where the system inherently becomes more complex because it can't do anything else. It's built into the system. It goes into a different kind of stability called dynamic kinetic stability, which derives out the second law of thermodynamics, but I'm not going to go into detail today with this, perhaps another time. So all this kerfuffle about how can we have a complex organism, how can it get from a simple zygote? The textbooks are arguing about it, about this, that, and everything else. They make all sorts of models. Biotensegrity has the answer by looking at all these different bits, putting them together, coupled with the bits that I'm not going to go into, which is a bit frustrating, I know, leads us to where we are now. Simple models, complex biology, get to the table, get to the toy shops, get the bits and make your own models because they help to explain so much. That's me done. Thank you.
And Graham, I'm going to take the spotlight off of you and invite Susan. I see her hand is raised. So I will invite her to start with her questions or comments. Meanwhile, I believe that Patricia will be passing you the questions in your chat.
Okay, thank you.
Graham, you have to know that Craig Nevin in the chat, and I will get to my question, said, probably the best presentation I have ever seen ever anywhere. So well done, Graham.
Oh, well, thank you, Craig. I'm glad you liked it.
When you showed that last, the model where you sort of inverted the tensegrity, right? And you changed the strings for struts. Do you not have a cuboctahedron there? Is there an idea of a cuboctahedron
It is. It
actually being a dual of the T icosa?
Yes. Yes.
In a way, right?
Yes, it's a dodecahedron. I didn't go into duality, but...
Well, wait a minute. A dodecahedron, it looks like a cuboctahedron. I'm seeing...
a cuboctahedron.
Yeah. Okay.
Yeah. It's where we started with the Jitterbug. It's a cuboctahedral outline. Yes, it's a cuboctahedron.
Exactly. So isn't that interesting? That again... sorry, I just want to say, isn't that interesting that again you have shapes generating shapes and we see the same patterns arising? Yeah. Sorry, I'll try to be quiet.
No, that's fine. The thing is, I was just playing to see what would happen. If I did the same thing with this, change each of, because it's more complex than the 6-strut one, if I did the same thing in this, what would it lead to? I don't know. So that's for the future. Or somebody else can beat me to it.
That's wonderful. Thank you so much.
Thanks, Susan.
Now, I don't know if we have other people with...
We do. We have a question from Anna, but is this a good time to invite people to turn their cameras back on, Susan, Graham?
Yes, sure.
And let's have a word from Steve first. Well, everybody does that. Go ahead, Steve.
Well, I'm just saying I can now sit back and relax because Graham takes over from here.
Well, it's all been inspired by your work. I must say that.
Well, I'm happy to succeed and let you do the work from here on. Back in the early days, I was using toothpicks and raisins, trying to do some of those same kind of things. And I didn't have enough hands and fingers to figure it all out. And that's when I got involved with Tom Flemons, who did a lot of the modeling for me and figured it out for me. And then, of course, Graham came in. And I remember seeing his first model and was overwhelmed by it. I didn't even know what to do with it. It looked like, something from an amputated limb of a knight still in armor. But I mean, he has certainly evolved from that point.
Yes, I remember the night when I was shaking with my knees at the time to meet the master.
Well, Graham, I've seen so many more. I've seen a lot of your models, but I've seen so many more of them. And I would love to see them moving. I would love to get my hands on them. So I think we have more models for eventually when we have a location for the archive, because I think other people would see the same. It's fascinating to see more about how you're learning. It's
and
incredible.
More model building workshops.
Yes,
yeah.
And the more you play with them, you don't know where you're going to get to. You don't know what you're going to find, which is why it's so important to get hold of them, build them. Because when you play with them, you think of things and how it relates to the body. I mean, think of things about how it relates to the body. It's not modeling anatomy, it's stimulating ideas. And that's what we all need, because we've all been brought up with the idea of the lever model. And we have to look to new stuff.
And that's such an important thing that you're talking about, is the models are models for inspiration, for learning. And I know we have had a discussion about cadavers, or I know, Mariana, you used the pieces of chicken in your presentation for sneak peek for the Congress this weekend. And we can see those as well as models. Is that right? Because they're not quite living anymore, so they don't have all of the same properties as living organisms.
Anything that gets you closer to understanding how the body really is useful, no matter what it is.
Well, and that's, I don't know how you can get closer than that.
So then
Yeah.
this is Leftheri-Pavlidis dactylognosis, the learning through the fingertips.
Yes, yes.
Graham's talking about, yeah.
Okay, Graham, did you want, I know Anna Kroll has a question. So Anna, is it okay if we invite Anna to turn on her camera here? She's on. Go ahead, Anna.
Hiya, Graham. It was just about, you had a couple of particularly great models that I wonder how to get hold of them. One you referred to as influenced by Penrose, and the one that you showed just after that I think you called the Janssen mechanism. How have you made them, or have you bought them?
I made this. This one here, I presume you're talking about. Is that right?
Yeah, yeah.
It was produced by Junichi Yanonose. That's Junichi Yanonose in Japan, who's a mathematician who makes all sorts of models. I should have thought of this beforehand.
Well, Graham, if we put his name, if you can put his name in the chat. I know it's also in your book, and it's probably on your website, right?
You can find a link to it, possibly. I'm not sure. I'll put it in the chat.
Definitely in your book. If you put it in the chat, people can look up his work, I think, right?
Yes, you have to find, because the main place his stuff is, and it's come to me as I write it in. So Junichi Yan and O's, and you'll put that name in, and you have to go through a series of links before you get to the website where he shows a much bigger one of these.
Can I also say that we'll be doing another newsletter next week with follow-up stuff. So if there's any link that you can't find now that you want to be able to give people, we can throw that in.
Yes.
And I put the link, sorry, Graham, I put the link for the strand base model in the chat.
Okay, I'll come to that in a moment.
Right, okay. The strand base model.
This model I made.
Hang on, let me spotlight you, Graham.
All right, this model I made because Junichi gives a diagram of all different parts on this website. It's not his, it's on his website. So I printed it out, cut round all different shapes, then put it together with little rivet things. It was pretty sloppy, so I eventually redrew the pattern and gave it to a 3D printer, and they printed it out, and then I put the thing together. So it shows how closed kinematic chains interact. You know, think of this throughout the body.
Is it 3D printer or is it a laser cut?
Sorry, laser cut. It was laser cut. Technology is working faster than I can keep up with. Yes, it was laser printed. The Janssen mechanism, you'll find this on various websites. There's also a lot of spurious stuff out there with the wrong measurements, which send you down the completely wrong way, because if they're not precise measurements, it just won't work. So I will also send you details of that as well, because once you find out how to make the Janssen mechanism, and it's fiddly because these pivots here, you know, technically a bit difficult to make. I must emphasize that I started my life as a lab technician, fiddling with test tubes and bits of string and tubes and all stuff. That's where I made models of airplanes as a child. So that's where I get the practical ability. But anybody can make this stuff. You can. Okay, Chris.
Thanks, Graham.
Thanks, Anna.
And Mariana has her hand up. No?
There are some questions before me, so it's okay. I'll wait my turn.
Okay, are you going to be, Mariana, will you let Graham know who and unmute everyone as you're doing that? Since I made a slight mistake and I understand you're monitoring the questions today. So you can just jump in and I will keep myself unmuted. I mean, I will mute myself if you're prepared to do that.
Yes. I guess I'll go because there were just comments, Graham, like how wonderful this presentation is. I'm just revising again because I thought I had one more comment, but it was Anna's actually.
So I can go on waffling forever.
Yes. Yes, I just wanted to say that with your cranial model, that I absolutely love it, and I can relate to that. That's one of the things that made me go into understanding the cranial movement for these kids, because in my case, all the kids that I work with, is never round, it's never a vault, it's always like they're different. There are many asymmetries there. But for me, it's crucial how that is related to the rest of the body. And when I'm there, I can clearly see how everything is connected, and I can clearly like understand what I'm doing with my hands and how that is going all the way to the feet, for example. So I'm always, and then linking that to the spine, like you should take all your models and just link them together. That's gonna give us like an even better understanding, because now you're talking about the hyoid bone, and I feel there is a clear relation with the base of the skull, but also with the abdomen as well. So I'm working there with my hands, and now and I guess you're right. This understanding with your hands, playing with the models, opens your mind to pay attention to other parts in the body, even though there is no specific anatomical relationship described. And even if there are now coming with more relationships, in my kids, they don't show that. They don't show what the book says. So me being open-minded, having the Tensegrity model in my head is what's guiding me to, okay, where is this coming from? And that only comes from the model. So yes, absolutely. It's not a question, it's just a comment. So I just love your models. Thank you.
Yes, thank you, Maria. That's quite right. It's before I just came across Biotensegrity, I've been practicing for several years, and I did what I've been told, and with practice you get experience to do things, and I would be working on somebody at one place and things would be happening at the other end. I'm working on the left shoulder, and the right knee would start doing things. The patient would describe it to me. I thought, well, how's that work then? I know it's all connected, but I wanted to know more of that. So it was like a flashing a light when I read that article, saw that picture. This is something different. It just blew my mind, because it didn't change my approach to treatment, but it made me more confident of what I was doing, because now I had a better model to explain to myself and my clients, patients, what I was doing, which was very reinforced itself, because I think they got a better treatment since then. I don't know how you quantify it at all, but understanding the basic principles, understanding that lever model is old hat, it's way old hat, and so much more as well. This new thing of Biotensegrity just gave me a bit of understanding, and we can get very excited about it. So keep grounded with the basic stuff, the geodesic geometry, the close packing, the minimal energy.
And thanks, I will add to that my newer addition to this is understanding soft matter, because then that's another layer of understanding what's going on with all those tissues that are soft matter.
Oh, yes.
Behave different. So that's my next step, like putting all this together into a bigger picture now. We do have more questions now coming in. So I don't know if you want to read it here. It's a very, or Fiona, should I unmute you so you can ask this?
Hey, hold on, Mariana. There's a question about what the model is that, not that Leah was, let's see, it was before that. Barbara Rosamilla was asking about what is the little toy, the second one just before the Jitterbug. I just want to make sure we got that toy identified. I don't know if it was the Hoberman sphere.
There's this one here. Was it that one?
Barbara, where are you?
She's in the middle of my screen. She's muted.
She says that one. Yes, she said in the chat, that one. Mm-hmm.
I can't remember what it's called. It's called something that doesn't relate anything like to what it is.
We'll look for it, Barbara. We'll look for it.
Put a Google search for Hoberman sphere, and it'll come up as something related to it, I'm sure. I think that's how I found it. It's not a tensegrity, but it shows that auxetic behavior and the twist as well.
Yes, thank you. Sorry, back to you, Mariana.
There is this question from Fiona, so I'm going to unmute you, Fiona, so you can.
Thanks, Mariana.
Hello, Fiona.
Hi there. Thanks so much for that wonderful presentation. It's so good. It's so excellent to have this practicality of the models and what they mean for biotensegrity. And that is what is so difficult to articulate when it comes to speaking to people, whether you're doing a talk or you're just talking to clients. It's fantastic. It's so important. Anyway, so it was just a question. I understand that the geodesic domes can be an ever-increasing kind of circular spherical shape. But so when that comes to biology, in biology, is there ever anything that's truly circular, or is it the principle of that architecture of tensegrity?
There's nothing is truly spherical. Nothing in the universe is truly spherical. Because if you get the microscope and look at the surface, there'll always be little bumps about it. And the icosahedron, the high frequency icosahedron or higher order icosahedron, is a shape that most closely matches that of a sphere. Now we could argue about the dodecahedron occupies a greater volume than the standard icosahedron. But if you take it to the higher frequency where divide the triangular faces into smaller ones until eventually it looks like a sphere, that gets closer to it. You can see the icosahedron literally in spherical viruses. The coronavirus is an icosahedral virus, icosahedral symmetries. Something within cells called, I can forget what they're called, but they very closely match a truncated icosahedron. That's where some of the vertices of the icosahedron have been cut off. And there's something to do with the transfer of or secretion of something inside the cell outwards. I can't think what the name of them is. They're microscopic things anyway. Otherwise, I don't think you won't see literally tensegrities, and otherwise you won't see true icosahedron or tetrahedra. They're representations of, get us in the place of how to think about it. These simple shapes. The icosahedron, the high frequency icosahedron, occupies a maximum volume in the minimum surface area. The tetrahedron, with all those helixes, occupies the minimum surface area within maximum volume. No, minimum volume than the maximum surface area. So that two ends of the spectrum. Anyway, I digress. Did I answer your question, Fiona? I've forgotten now.
Yes, it does, because there's obviously from the micro to the macro, just everything, the cytoskeleton within the cell, and then there's the relationship of each cells. And I'll just even, it's difficult to kind of think about everything being in, because even the cell membrane will have some kind of
endocytosis. Endocytosis is a mechanism why producing these regular shapes. So Google search might get you close to it.
Yeah, thank you. Wonderful.
Ram, we have a question from YouTube. Neo posted it here. I'm going to read it for you. And I lost it again. Okay, hold on, it's coming. Sorry for this. Okay, it says from Stickfa Fighter. That's the name from YouTube.
Okay.
These models are super helpful in understanding the concept. Do you have a goal of creating a complete model of the human body? I wish.
No, because that's impossible. The only complete model of the human body is us. We might think we get close to it, but we'll never get close to it because it's just so enormously complex and the whole thing works in unison. And the models get us into understanding parts of it, different aspects of it. That's why every model is different. There's no limit to number of models we can make, because each one will show something different, give us a clue into understanding it. So we can make robots and all that, but the simplicity of the most complex robot, the most complex computer is just nothing compared to the human body. Now come back in 200 years' time, maybe we're getting closer, but I don't think so. I don't think so.
Great. So Patricia, you have your question there?
Yeah, so I have a question. It has to do with me being kind of a novice model builder. And I run into two issues when I try to make models. One is kind of a technical issue where I have a lot of failures in getting it to like hold together. And I'm not going to ask you to address that so much, although I've found that just being more comfortable with the idea of failure helps with that. And but the other question is, are there a basic set of questions that you can advise a novice like me to ask when I start interacting with a new model? Because sometimes I start to work with it and then I just kind of get, after my initial observations, I get a little bogged down because I'm not as creative as you or Mariana and sort of like really exploring the model. So I'm imagining that, like, watching you interact with the models today, I imagine that one question might be, what happens to the whole structure when I bring 2 points closer together or when I bring 2 points farther apart from each other? But are there other questions that are just kind of like basic exploratory questions that someone like me can use and apply to every model I build, just as a starting point to get my brain working?
Okay, Patricia. Well, your brain is already working. It's already churning over things. Everything happens in relation to everything else. So the whole process is a process of development to greater complexity of understanding. And the more you learn from the textbooks, I like textbooks for pictures. I prefer the scientific papers for the nitty gritty. Textbooks are so waffly for me. But just getting to the what's out there, and it's just so much. I haven't evaded your question, I'll come back to it. There's so much out there in the literature that supports the biotensegrity concept. It's just that it's not been recognized before. So it's a two-way process. I might think of a question about the body and then try and make a model to illustrate that. Or it might be I'm just playing with a model. Oh, I see this in a thing in a toy shop. Wonder if that's interesting or not, and play with it. Oh, that gives me ideas about this. And it goes on and on. For years and years and years, many years, I hadn't got a clue about biotensegrity. I didn't understand it. I thought I knew it. This is my understanding of biotensegrity. And I didn't really, but I stuck with it. I still don't know. I know there is no limit to understanding it. It's an ongoing process. There's no expert apart from we're all experts on a different part of the pathway to learning. So playing with, sorry?
I just want to chip in on that model question.
Yeah.
Is that I think it's pretty well documented when we're in a state of play, as you said, Graham, that's when we kind of learn the fastest, the most. We learn at levels we don't even know we're learning at. So I think it's what you said. You build them, you play with them, and then things come out that you couldn't have expected. And it's fine to ask a question as well and go into the model that way. But sometimes it's just listening, and that's when the unexpected can come.
Yes.
Do you find?
Absolutely. And to add to Patricia's question, if you've got a model, it's not going right, put it aside and do something else. I've got models that I made many years ago. I had no idea what the significance was. It was only later I thought, oh, perhaps that can, yes, dig it out, refine it. And suddenly it became useful. And of course, you've got to have somewhere to put these things, because shelves soon get dusty, cupboards soon get full. I've got hundreds of these things, but then that's what houses are for, to put tensegrity models in. So it is a matter of, and if you can, I know we can't right now, do them with other people on Zoom and stuff even, make models together, you get your successes and you get your failures. We all do. And sometimes it can take weeks and weeks to make one model work, just the technicalities of making it. But then we all have to start somewhere. You've already made models, I'm sure. If they're not complete, then you made models. You're on your way.
Gregory? Sorry, Neil.
Yes, Neil.
Yes. Yes, just to kind of piggyback on the question that came from YouTube by Stickfoot Fighter. Do you see this knowledge that we're coming on or that we're experiencing and getting from Biotensegrity, do you see it kind of leading into us being able to build a human model?
No. We can build robots, and they might be able to do all sorts of things that we can do. It'll never be a human model. I
did put in the chat a link to a guy that you can see it on YouTube, where he's taken a whole entire skeleton and done this. Maybe somebody can put it into YouTube as well for that question that came from there.
Oh, yes,
it's the bone man person. Sorry.
Yes, he's in Germany. And yes, it's a great tensegrity model. For myself, I'm not interested, that's personally speaking, I'm not interested in making anatomical models. For myself, I'm interested in making models that stimulate ideas that relate to the anatomy. Now, other people might work the other way around. They might want to make a tensegrity, whatever it is. And that's great if that's their way in. But we have to distinguish between them. And with models, we have all the models I've shown have strings which are the same length. They're not stretchable. They're fixed string lengths. As opposed to the stretchy string models, which there's lots of them around, and they're great, which are representations of the anatomy, and they're fine for understanding something, for explaining it. They're great. But for understanding the basic principles, it's just fixed string models, which I think are most important. And if you've got a section of both, even better still. But make sure you've got the fixed string ones as well. And
Carol, I'm unmuting you so you can
thank you,
ask. Yeah.
Graham, that was brilliant. And I just can't tell you how excited I am now to contemplate what you've taught us about the cranial dynamics. You know, when I was a physical therapy student, I was told that I had to believe that the cranial plates fused, and that anybody said that they felt anything in the cranium was hallucinating. And then I took a look at the cranial bones, a model of the cranial bones, and I saw that sliding in the between where the bones articulate. And I thought, well, why would there be sliding if they were fused? And then, of course, we learned that, well, what you're actually feeling is the flow of the craniosacral rhythm, the cerebral spinal fluid flowing underneath the cranium and on top of the meninges, between the dura and the meninges. And for me, that wasn't what I felt at all. It wasn't a flow. It was much more this dynamic push-pull kind of thing that you showed so beautifully in your diagrams. And it just all came together for me. Finally, 52 years in practice, I finally get an illustration of what my hands have been feeling for 30 years. And I just want to thank you so much for that.
Thank you, Carol. There's a couple of things I want to add on to that. Yes, it's widely thought that the bones are fused. It's also been shown that the bones can remain completely patent. The sutures maintain that space throughout life. And many skulls that on the outside look as though they're fused are actually just a thin veneer, because living bone isn't fixed, hard and solid. Even living bone is flexible to a certain degree. So what may look like a fused suture on the outside, from the inside, has still got that flexibility about it.
Yeah.
I also say that the cranial rhythmic impulse that osteopaths have recognized for nearly 100 years, and craniosacral therapists, that's the same frequency as matches the blood pressure waves, the Maya waves that are palpated in the limb. Now, anybody can feel this, but it takes practice. And I say, don't go practicing. Once you start, you need to need training before you start working with it, because otherwise you're dabbling in things. It's very gentle techniques, but they're also very powerful as well. So I must emphasize this medical caution at the end of the session. So, thank you, Carol.
Thank you.
Nobody wants to talk, I can waffle on for more. So I was mentioning about soft matter. I haven't mentioned soft matter, so I think I've forgotten who mentioned it now. Susan mentioned it, somebody else mentioned it. Soft matter.
It was Mariana.
Mariana, thank you, Mariana. Yes, soft matter is a new field of physics research of which living tissues portray soft matter. Now, soft matter is different from hard matter physics, where it's hugely complex. It's a vast open field with so many people getting in, very complicated, where the tissues themselves undergo phase changes. So rather than having a solid, like a hard bone, and a soft tissue, soft matter doesn't just relate to soft tissues, it relates to all living tissue that can change phase from one state to another. Think of liquid crystals, which can form what's called a solid phase, or it's not really solid, and then a gel phase, more a liquid phase. So they can change from one to the other through mechanical force or change in temperature or electrical signal. And this is what's happening in the body at the time. But the field of soft matter hasn't been around long enough to really make big inroads into biotensegrity, but biotensegrity and the two are intimately joined. We haven't made a lot of connections with the literature yet and the researchers. But soft matter is a thing, it's a way forward.
Sorry, Chris, go ahead.
I am curious to know, Graham, and I'm sure there are a lot of people here that feel the same. What is your current area of exploration in terms of models that you're making, and what you're hoping to find out? What are you exploring right now?
I've been writing something recently on superstability, so I wanted to know more about it, and I find the best way to learn is to write. So I read a lot of literature, talk to people, and then write it out in a way that I hope I can understand. And in the process, I was going to write the whole thing planned out. And in the process, I have got a section on stability, general stability. What's that all about? Well, that should do a few paragraphs, and I can get back to the nitty gritty. And I discovered that stability is far more complicated than I ever thought possible, but in a good way. There's many different types of stability, and each one has is appropriate to a different circumstance. So I'm on the fly here. We'll see how we get on. So my quest into stability took me to the second law of thermodynamics, which says that energy always, I paraphrase it, energy always flows towards a more stable system, towards a point of equilibrium. The change always goes from a less stable system to a more stable system. Once it gets there, it can't change on its own. Everything in the universe follows the second law of thermodynamics and progresses towards a state of equilibrium. Except living structures, humans, exist in states that are far from equilibrium. They can keep going. They don't collapse into states of equilibrium until after they've died. What's going on here? Now, the direction of, are we okay with time for this? Because it might take a few minutes.
Yes, go, go, go. Great.
We're super interested in hearing this, Graham.
If it collapses, we'll see. We'll see how far we get with this. So energy, all systems always go from a less stable state to a more stable state. It's inherent in the definition of stability, the persistence in time. And Boltzmann introduced the concept of entropy, which is not about disorder. It's about number of degrees of freedom, or multiple states within the system, or possibilities within the system.
Graham, can we get that name? Is that Sharon Glotzer, are you saying?
Say it again.
Was that Sharon Glotzer's work?
No, I do value her work, but I wasn't thinking of that particularly.
What was the name you said? I
didn't remember. I did say a name.
Oh, okay. Okay. Sorry. I must have misheard.
But I'll throw you a name anyway, which is Pascal and Pross. Pascal and Pross. Look them up. We'll come to that in a moment. So, where were we? Entropy. Entropy is a measure of the number of degrees of freedom or microstates within the system, number of possibilities. And it has a, what's the word? Probabilistic nature about it. So it transfers the less stable state to a more stable state, to a less probable to more probable. So every system goes from a system will work from being a less stable, less probable state to a more probable state. All right. Well, I have to introduce Pascal and Pross in here because they recognize some of these changes. It means that the second law of thermodynamics has two consequences. One is an energetic stability, but also persistent stability. So a system can persist, which is not necessarily energetically stable, as living organisms are. And they demonstrated that a self-replicating population that's increasing in, is growing, increasing in size exponentially, is also controlling its own growth. It's self-catalyzing its own system. It reproduces itself. And we have human populations do this. It's like a Malthusian population where the system, as long as you keep feeding nutrients in, it'll keep growing. There's natural constraints within the system that stop it growing forever and ever. And the molecular system is a huge, metabolism is a huge molecular system where everything's changing all the time, but it's all interlinked. It's making its own copies of its own self. It enables the system to overcome and circumvent kinetic barriers. Now, kinetic barriers, as an example, we take hydrogen and oxygen. We have a tank of hydrogen and oxygen at room temperature. And we put a catalyst in that, and the whole thing will go bang and explode and produce water. It naturally does that automatically. But if we freeze that hydrogen and oxygen down to much lower temperature and don't put a catalyst in, the hydrogen and oxygen will stay there forever. They'll never react together because the kinetic barrier can't be overcome, or rather the kinetic barrier is there to stop them going towards the state of energetic stability. So I'll just recap. We've got energetic stability and persistent stability. So the hydrogen and oxygen form a persistently stable system. Not energetically stable, but persistently stable. And living systems do that. And an inherent characteristic of self-replicating systems that can produce copies of themselves is that they become more complex. It's inherent within the system. They can't do anything else. So a system will become more and more complex. So we have a single cell or a zygote. Sorry, Yaf, if you're watching, we have a zygote. And through embryology, it becomes more complex because it can't do anything else. Now, this is something that Pascal and Pross have been promoting for a few years. It's out there, there's lots of stuff out there, but it's not recognized as, I don't know. But it seems crucially important because it applies directly to biotensegrity, to biology. The system can't help but become more complex. Embryology is an evolutionary process. The whole system is developing, growing, because it can't do anything else. As long as we shovel food into it, it'll carry on doing that. And the whole of life has a transition during birth, naturally, from one state to another, but it keeps on doing that. But of course, lots of things get in the way. It circumvents so many kinetic barriers to maintain itself till eventually the whole thing croaks up and we die, because that's a natural way. Whether that can be extended from knowing about these things in the future, I don't know. But I throw this in because that's what I'm working on, trying to understand this thing about stability, complexity, embryology, biotensegrity, which are all intertwined, interrelated together. There's a long way to go. The thing I thought I was writing is now hugely vast, but that's the nature of it.
Another book, maybe, Graham. I appreciate in your presentation how you really pointed out this fact that from simplicity, the complexity emerges. Would that be the correct way of saying that?
Complexity is inherent within the system, and it emerges. Yeah. Things emerge out of the complexity.
Thank you. Take me a while to process. I can't ask any more questions at the moment.
Well, I've got a pint of beer after all this.
We have, hold on, sorry, I'm not doing my job very well today.
Perhaps we're done, are we? I can keep going, but if we're done, we're done.
Perhaps we should go ahead.
I put a link to one of the Pascal and Prost papers in the chat so that people can, jump in and follow that thread. If they want to.
Barbara also had a specific question. I think that's what Mariana's looking for.
Thank you. Yes.
Yes, for Barbara's question. Maybe we can just unmute her.
Mariana, you going to do that so we don't double task here?
Yes, just did.
Thank you.
She needs to unmute though. I didn't see her face there, but I just asked to unmute.
2 minutes.
Or we can read the questions. Patricia, do you want to help me there? Sure. Well, do you suppose there is any relationship to the Schumann resonance frequency?
I have no idea. I'm not familiar with Schumann. I know the name, but I'm not familiar with them, I'm afraid.
Okay. Perhaps what we can do here is do our close and our sponsors. Graham, I don't know if you're up for the toast or not. I know you've been on the hot seat for a long time, but if you are, and then we can carry on to our after party and have more of our regular after party atmosphere.
Okay.
I just want to say I didn't really disappear, but I was looking for my Pershing book. Pershing won a Nobel Prize for this energy kind of thing and complexity. And it's a nice little book that you can get that sort of gets you into complexity.
Did you find it, Steve?
No, it's on my shelf someplace. I missed it.
This thing from Pascal and Prost actually takes Prigogine further as well. So by all means, do read that book. I haven't read it myself, but I'd like to.
Yeah.
We've got somebody asking for spelling of Prigogine. So let's.
You got me. If I find the book, I'll let you know.
Stephen Schafferman has given us the answer of the spelling. So thank you, Stephen. So let's. Susan, are you able to? Well, first of all, Graham, thank you. Thank you so much. I know people have been waiting to hear from you for a long time. And as we were talking earlier, watching what they can find over and over and over again. Now, this is going to give us a lot of material to work with. Yes, Mariana? And Susan, and fantastic. Thank you.
Thank you.
I don't usually say very much. Sorry, Graham.
I just say I don't usually say very much. So.
Well, we really appreciate you being willing to share, because what you have to say is so clear and step by step by step, and it always enables us to see new insights. So it's really important.
Oh, thank you, Chris. Thank you, everybody, for watching. Okay, Susan.
Susan, you want to let us know what's happening next week?
What's happening next week?
Anastasia, no?
Oh my gosh. Right? I thought you were asking me for the sponsor, so I was like,
okay, go for the sponsors. Is Anastasia here today?
I didn't see him, but yeah, next.
Okay, you go for the sponsors, and I'm gonna.
I'll say Chris Kresge, is a Feldenkrais kind of senior practitioner, and she's got a new book coming out from Handspring. It's an edited book. If Eleanor's still here, she might be able to say something about it because it's going to be. She had to leave. Maggie's is that what you're saying, Maggie? Yeah. Okay, because Eleanor's one of the contributors, and Anastasia, of course, is also a senior Feldenkrais teacher and a long time, aficionado of Biotensegrity. And so the three of them will be talking about Feldenkrais and Biotensegrity in this new Handspring book next week.
Excellent, thank you. Are you ready to do the sponsors as well?
Yes, and we will thank. Go ahead, Steve, go ahead.
Well, I just want to add, is my mic open, I think? Yeah, I just wanted to add that there was a big discussion about, what was the big discussion about, not springiness, but,
elasticity.
No, what?
Stretching.
Pardon?
Stretching.
Stretching. It was a big thing about stretching, and I just put a link on the chat for a very nice little video on stretching that has a contrary view that John had of it, but it shows that physiologists have conflicting views, and it's not easy to have a dogmatic opinion about anything. And as a matter of fact, pardon?
I'm looking for it.
I just put it. Oh, I haven't pushed the button here. There it goes.
Ah, there we go. It's the physics girl.
Yes, the physics girl thing.
I love the physics girl.
Yeah, and it does a nice little thing. You have to understand that all this is talking about hard matter physics. They're still, even though they're talking about springs, and stretching, they're in hard matter physics. And we now know that this is soft matter and auxetic, and it's probably even different than what they say. But even at that level, there's a lot of argument. So you can't believe, you have to question authority. That's key to it. Don't believe anything we say.
We don't see the link just yet.
You don't see the link?
Maybe you send it to someone privately. Just make sure that
it says to everyone. Let me see. I pushed it again. Here it is, to everyone.
Okay, now we see it.
Oh, now you see it. Okay.
Good. Yeah, I love Physics Girl. She's a lot of fun. Okay, we want to thanks Steve. Thanks Graham, thanks everybody. Thanks to all our volunteers, Handspring Publishing, Embodied Biotensegrity, WeFlow Therapy, the International Biotensegrity Congress that's happening right now, and that Mariana and Chris and I and Diane Woodruff and Kayla June and MJ Porter are all presenting.
And Maggie tomorrow too. I see Maggie on my screen. She's here.
I think Maggie's not tomorrow though. I was going to say that's tomorrow. And then on Sunday, I think Maggie, Anna Crowell, Doug Johnson, Selena. And so we've got a lot of fun people presenting on Sunday as well. The Fascia Hub, Matrix Repatterning, Integrated Biotensegrity, Pretensed, and Artifact Pro. And looking ahead, I know that Fabiana is going to be putting together another international fascia event like she did for last year. And maybe in the next week or two, we'll be hearing more about that. So that's what I've got. And I'm still looking for that little toy in Amazon. So that's another thing. If somebody can remind me, we'll put that in when we do the recap for the newsletter, we'll see if we can, by then we should have found the link.
Okay, excellent. Thank you. We always like to close with a toast. Graham, if you're up to it.
Yes, I propose a toast for biotensegrity, and may the gods give you the blessing of fiddly fingers to help you put tensegrity models together. Cheers.
Cheers. Cheers. Chin chin.